So now we've done the introductory stuff. The big theme, of course, of this extension material is a consideration of the reactivity of substituted benzene rings. Got a benzene ring? You're world experts on how benzene rings react. But what happens if you stick another group on that benzene ring? What happens if you have methylbenzene, otherwise known as toluene? What happens if you have chlorobenzene? How do the reactivity of these substituted benzenes compare to the reactivity of benzene itself? And we're going to think about that from two perspectives. The first is just the relative reactivity. Does putting a substituent on benzene make it react more quickly or less quickly than the original benzene? And then the second thing is that benzene, it didn't matter which carbon our attacking group, our electrophile, went on, because of course in benzene all carbons are identical. But as soon as you put a substituent onto a benzene ring, now you've defined that carbon as carbon 1. If you then do substitution of any of the hydrogens, will that substitution occur at carbon 2, carbon 3 or carbon 4? Okay, so we got to worry about the relative reactivity, and we have to worry about the so-called regioselectivity of the reaction. Start off with the relative reactivity. Okay, now let's think about why benzene reacts. It reacts because it's got a pi electron cloud that is attractive to an electrophile. So therefore, with our substituent, if it can put electrons into the ring, then the first thing that happens is that, of course, that electron cloud becomes more attractive to electrophiles because it's got more electron density. But the other, much more important consideration is that the intermediate, everything comes back to intermediates in this discussion. The intermediate of the reaction is a carbocation. Well, if you have a substituent that can put electrons into the ring, it can stabilize that carbocation intermediate. Now let's look at a fast reaction profile just to emphasize the effect on that. We've already seen that electrophilic aromatic substitution is a two-step process in which the first step is the slow step. In other words, the attacking of the benzene ring is that slow step, and then of course the faster step is once you've got that 4-coordinate non-aromatic, non-conjugated, non-delocalized intermediate. When I say non-delocalized, I mean all the electrons around it. Well, then it's much easier to get rid of that hydrogen as it leaves. Okay, so here's a typical reaction profile, and of course here's the activation energy, and here is our intermediate. Well, if we have a intermediate that's got more electrons coming into it from the substituent, that intermediate is a little bit more stable, lower energy, just like we said there. And notice also that the activation energy is going to be reduced. And I hope you remember from your kinetics that the lower the activation energy, the better the reaction. Now let's think about what this means in terms of what we know about possible substituents. We want electron density coming into the ring. So in other words, it's going to be nice if we have a substituent that has a positive inductive effect. It pushes electrons in rather than pulls electrons away. So you want a positive inductive effect. You also want, if you can, again, to increase the electron density in the ring, a positive mesomeric effect. And as we'll see, both of these are important, but more often than not, the mesomeric effect is more important than the inductive effect when we're talking about this big pi electron system, a benzene ring. So let's think about possibilities. Here are all the different types of groups, not all the different types of groups, but a selection of groups that might be attached to our benzene. And here are what we know about their inductive effects. Alkyl groups, so methyl, ethyl, or carbon-carbon double bonds, have positive inductive effects. But all these other groups have negative inductive effects. If you've got a oxygen or a nitrogen or a sulfur bonded to the ring, well then that's more electronegative than carbon. It's going to pull electrons away. Halogens, of course, with the exception really of iodine, more electronegative than carbon. They're going to pull electrons away. If you've got a carbon bonded to the ring, double bonded to an oxygen, it will pull electrons away. Nitrogens will pull electrons away. We've already seen carbon bonded to nitrogen will pull electrons away. So not many things have got that positive inductive, quite a lot of the possible groups negative inductive. But now when we look at the mesomeric effects, alkyl groups don't have any pi electrons, so no mesomeric effect. Alkenes, positive mesomeric effect. We've got, of course, these groups down here with the negative mesomeric effect. So we can immediately say that alkyl groups are going to be good. You've got a positive inductive effect, no mesomeric effect. It's going to activate the ring. Okay, it's going to put electrons into the ring. It's going to activate the ring. It will be more reactive. Carbon-carbon double bonds, of course, they've got positive inductive and positive mesomeric effects. They too will be activating of the ring. So toluene, methylbenzene, should be more reactive than benzene. Down the other end of the scale, got a whole bunch of things that have negative inductive and negative mesomeric. They're going to undoubtedly deactivate the ring. They'll just be sucking electron density away from the ring like crazy, making it less reactive. Less reactive because it's less attractive to electrophiles, and less reactive because it will destabilize the carbocation relative to benzene. Okay, so for example, a benzene ring with a cyanide on it, a benzene ring that has an acid group on it, benzoic acid, these are all less reactive than benzene. Now it's these ones here that are kind of interesting, where you have a bad inductive effect but a nice mesomeric effect. And most groups, as I said, mesomeric effects are usually bigger than inductive effects. So most groups here, like OH, OR, SR, NH2, NR2, and so on, because the mesomeric effect, the nice mesomeric effect, is bigger than the nasty inductive effect, these will end up being activating. But halogens are unique. Hate to use the word unique, but we'll use it here. Halogens are unique in that, yes, they've got negative inductive and positive mesomeric, but the negative inductive is actually bigger than the positive mesomeric. So overall, halogens are deactivators for the ring. So nothing you could really have predicted on some of these middle ones, but you've seen it, and it's important that you at least realize you've seen it and take it into the rest of them. Alkyl groups, carbon-carbon double bonds, activate because there is nothing bad about their presence. Groups such as carboxylic acid groups, cyanides, and so forth, there is nothing good about their presence. They will deactivate. But the rest, which is actually most important groups, when you have a electronegative atom like an oxygen or a nitrogen or a sulfur attached directly to the carbon, but those have lone pairs, so they have negative inductive but positive mesomeric, because the positive mesomeric is better than the negative inductive, they end up activating. Halogens, all on their own, they deactivate even though they've got positive mesomeric, because their negative inductive, they're sucking electrons away from the ring, outweighs their ability to put lone pairs in to help stabilize the intermediate.